I'm joined today by Dr. Chris Hunt from the National Physical Laboratory down in London. Welcome, Chris.
Hello, Trevor, and it's good to be here. Thanks. Thank you.
Now, you're always working on exciting research projects, and there's three of them that I want to touch on very briefly today. The first of which is, of course, working with high materials that are working in high thermal excursions, and you're working with things that are a bit like conductive adhesives. Can you tell us a bit about that project?
So the industries like oil industry, avionics, automotive are increasingly wanting to locate electronics in sort of high temperature regimes, and this is taking them beyond sort of the normal lead-free solders, and the current solder alternatives are lead tin alloys, but they're not easy to work with, and there are potential reliability issues around that. So people are interested in looking for alternative solutions. And one such solution that we've been pursuing with the consortium is around conductive adhesives. So these are two-component resin systems, which the project has a target for these to work at least 225 and hopefully 250. So they're metal or silver flake-loaded systems, and we're looking at the reliability of those systems at NPL.
So you're developing these for use at higher temperatures. In the past, a lot of conductive adhesives have been developed for the assembly process, where you're working with components that are a bit sensitive and can't withstand high excursions. But you're taking a different approach to this.
Yeah. So the beauty of these systems is that they're still going to be processed or cured at around a typical conductive adhesive temperature of around 150 degrees. But once you've cross-linked or cured the system, then you'll be able to operate at these elevated temperatures above 200 degrees.
I understand. Okay. So one of the other areas I want to talk about, Chris, is wearables. It's a very topical area at the moment. A lot of different people using things like silver strands woven into the cloth, etc. You have a different approach.
Yeah, so we have a patent pending technology where we can add our conductive material onto the fabric. So we could take a finished article of clothing, such as what I'm wearing today, and we can add our conductive technology onto that. So we could have 100% coverage of the fabric, or we can pattern it. So we could effectively write the same sort of artwork that you see on a printed circuit board, but we could write that onto your clothing. So we could distribute sensors, your microcontroller, your comms device, your battery, and you could have your clothing now turns into an electronic system which you can walk around with. But the nice thing about our technology is that we can apply it to more or less every fabric, and it doesn't affect the flexibility or the wearability. It still breathes, it still flexes, it still stretches, like your clothing did originally.
So you're effectively printing the printed circuit board onto the fabric using your material. But what then gives the structure for mounting the microcontrollers to that, for example? I mean, they need something to support them.
Right. So the circuit assembly, the microcontroller could be on a small board, which that has to be mounted to perhaps in a little package somewhere on the clothing. So, for example, rugby players, you can see they have a little patch or pack at the back between their shoulder blades. So what we can do is to embed all our intelligence and comms devices in that little package, so it's in an out of the way place, not really affecting the wearability of the garment, but all the active parts of the wearable system are now distributed around the rest of the garment, and they're connected back to that pack by our technology.
Okay. Well, that's very interesting. So we're interested to see the different applications you come out with on that one.
Yeah, so sort of defence, health, sports, fashion, are all potentially opportunities for this type of technology.
Fascinating. Now, very quickly, the last area I want to talk on is a new project that you've taken on basically humidity environments and a different way of testing. Can you talk to us about that?
So particularly for automotive and avionics guys, there are issues with their electronic systems being exposed in an environment below the dew point. And at that condition, we see condensation like we see on our cars in the morning during this time of the year. And if that occurs on a circuit board that isn't properly protected, that will lead to an instantaneous electrical short and failure. So people can take design remedies to try to prevent that being a problem, or they can actually conformally coat. This project that we're developing is to look at the efficacy of the coating process to see that you get sharp edge coverage. And we at MPL have developed a new test method to do this, and we have a substrate system which you mount your test vehicle on, and we can cool that to the dew point or just below, and we can hold this condition for indefinitely. So we can very carefully put on a condensation level layer, a water layer, and take it on and off repeatedly on demand as to what we want to do.
You can do that pretty accurately. You can really accurately control it.
Yeah, so the substrate temperature can be controlled to plus or minus 0.1, 0.2 degrees. It's sitting in the ambient humidity chamber at, say, 40 degrees. So we can step down in say, half-degree steps, for example, and you can see at a certain point, suddenly the humidity forms and the resistance of the system will drop suddenly.
Well, it's very interesting because, especially in car automotive applications in India and where I live in Florida, that's a problem.
Yeah, and we're well represented by the automotive industry in this project, so it's really exciting, and hoping for some really good data to come out of this.
And of course, all these great technologies you're hearing about today are going to appear in written articles in Global SMT going forward. Chris, it's been great to speak to you. Thanks for joining us today.
My pleasure. Thank you very much, Trevor.